Okay, now we'll begin with our section 4.8, which is about the analysis of deformation. So what we say is this. So thus far in this chapter, we have considered the force balance at a point within a stressed body. Okay, and the results which have been obtained were based on the requirement of equilibrium and are equally true for a hypothetical rigid body or for a real body which deforms under the action of stress. Our concern is with the real deformable bodies, and therefore in addition to establishing the conditions imposed by the force balance, we must determine what restrictions the requirement of a geometric compatibility imposes. Now, if I would want to take you back to 2.1, the first one was about the force equilibrium, the second one was about geometric compatibility. So what we have done is we have discussed about stress vector and tensor and things like that before, which were building up from force. Okay, we would now also want to build up some new quantities, which is the strain. Okay, coming out from displacements. One of the very important things about this is that the theory of stress, which you have just learned, is completely independent from the theory of strain. Meaning you will see the development of stress which has happened. Remember how we have taken the forces and planes and so on, and how the development of strain will happen in the following discussions. They are completely independent of each other. It's just like they are two separate animals out there. Okay, it does not mean that there is no relation between stress and strain. There is, but the theory and the definitions of these two things are completely different. So please follow this analysis of deformation. Eventually will lead to strains, and you will see that it's practically independent of each other how we develop these two theories of stress and strain. So stress we have already discussed. Now is the time for strains. Okay, so geometric compatibility imposes conditions of deformation, and we want to study that. So one of the things about geometric compatibility is of a continuous body is that in which there is no voids are created, no voids. So if you have, say, a piece of paper and you have or a piece of solid, whatever works, and you want to apply, you have applied certain loads on it, they can definitely deform. This can happen, right? So this is a geometric compatibility, but this cannot happen. This is a void. I mean, your material cannot tear. So this cannot happen, this can happen. So this is what we mean by geometric compatibility. Now this is purely based on in the problem of geometry of continuum and is independent of the equilibrium requirements established. So this not happening and this being allowed has got nothing to do with forces and equilibrium. It is how we take the geometric compatibility in our analysis for a continuous solid. Okay, has nothing to do with what we have learned before. Now let's begin our study by considering a continuous three-dimensional body. Okay, here you have a continuous three-dimensional body, and figure this undergoes a displacement such that point 1 goes to 1 dash. Okay, this point has gone to 1 dash, 2 has gone to 2 dash, 3 has gone to 3 dash, 4 has gone to 4 dash, ith point has gone to ith dash, and n has gone to nth dash. The point O has gone to O dash, and the dashed line which you see is the deformed state of the solid. Okay, so after the deformation has happened, this is how this three-dimensional solid looks like. Okay, so the displacements are clearly shown. Now one of the things is that all these displacements are shown as a vector. U1 in a bold symbol means a vector, and so on. U2, U3, U4, and so on. Okay, this should also have been a bold sign, so you can make that correction in your textbook. This should also have been a bold sign. Okay, this should also have been a bold sign, so you can make all these corrections in your book. So UI and U4 and U0, U1, U2, 3, U3 seems to be okay. Okay, UN is also okay, coming from N to N dash. One of the things is that the nth UN, because it's a vector, has been written as a vector. So UN is given as UNI cap plus VNJ cap plus WNK cap. Okay, so UN as a vector is this. UN, this is the scalar component with the in the x direction, scalar component in the y direction, this is in the z direction. Okay, so this is the components of this displacement of point n. Okay. Now one of the things is that the displacement of a continuous body can be considered as a sum of two parts, a translation and or rotation of the body as a whole and the motion of the points of the body relative to each other. So first part, translation or rotation, translation and or rotation, so either of them is possible, and or both is also possible, of body as a whole. So if you want to understand what this sentence is, take your pen, mobile phone, or whatever you have in front of you and just try to rotate it. Okay, rotate it any way you want. This is rotation of this body as a whole. Try to move it in any of the planes in any direction around. That is what a translation is. So this is a translation, rotation of the body as a whole. The second part about the displacement is the motion of points of body relative to each other. Okay, so the motion of the points of the body relative to each other. The translation rotation of the body as a whole is called rigid body motion, because it can take place even if the body is perfectly rigid. But the second part can only happen for a deformable body. How does a deformable body look like? Like this. Okay. In a rigid body, all these displacements u1, u2, u3 will all be exactly zero. None of the points will displace anywhere. Okay. So in figure 4.26 A, okay, 4.26A, we illustrate a rigid body translation of a triangle which is constrained to move only in the xy plane. So your triangle is ABC, and the rigid body translation of this is such that A goes to A dash, C goes to C dash, B goes to B dash. Okay, about the corner C. Okay, so sorry, move in the xy plane. So it has only moved. So it seems all of it has only moved up. Okay, because it can move only in the xy plane. Okay, now into 4.26b, we have a rigid body rotation about the center, uh, about the corner C. So you see C and C dash are the same. Okay, and A has moved to A dash, B has moved to B dash. So there's a rotation about this point C. This is again rigid body. So this is translation rigid body, this is rotation rigid body, and then 4.26C will be illustration of a deformation without rigid body motion. Okay, so there is no rigid body motion in this, but there is a deformation. So A has moved to A dash, B has moved to B dash, C has moved to C dash. So you see that the body is being pulled out, hence it is being deformed. Okay, it is increasing in size over here. In the other two cases, there is no increase in size, there is no there is no change in shape or dimensions anywhere. It was rigid. Here it is deformable, elastic solid, which we'll call later on. Now the displacements of figure 4.26D is the resultant of three displacements. Okay. Now this is the case where both A plus B and C has happened. So that's why you get this sort of a skewed idea. It's rotated, it has increased in size, it has translated. Okay, so lots of things have happened over here. And this is what we mean that the displacement in general is a combination of 1 and 2. Okay, so moving ahead, we say that the displacements associated with rigid body motion can be either large or small, while the displacements associated with deformation usually are small. So this one can be either large or small, but this for at least our course will always be small. And this is something we have done already in chapter 2 and 3. Remember the argument that the displacement was small and things like that, and the extension of the bar was small, and then we took an assumption that the arc can be replaced by the tangent. So we have already done all that. We continue with the same analogy over here, same analysis over here, that the motion of points of the body relative to each other will be small, but this it can have a large or a small translation rotation. It doesn't really matter us over here. Okay, so this is a chapter which actually matters in something called the dynamics, where you have the accelerations and vibrations into picture, and that will be dealt out in a course which is separate than this, perhaps in a course in vibrations. Now this is what is important to us, this 2 over here, or this part. Okay, this is something we ignore in this course. Actually you have done enough of it in mechanics 1 as well, the first year course. So this is what is important to us right now, and the rest of our course will only be about this. We will rarely have a case in which your solid body will be translating or rotating as a whole. Okay, so this is what we refer to, where the points are displacing relative to each other. And all this is what we want to say is that we have to study the deformation at a point in a continuous body. This is very similar to the forces and the stresses which were acting at a point in that body. So we are taking and defining all this at a point, at a specific point. And we will continue now to develop a theory of strain, define what strain is, again at a point. Okay. So stress and strain are all only relevant at a point. Even when we say the stress in the previous analysis, stress acting on this plane or that plane, yes, the stress is acting on that plane, but that is only for the sake of direction. The point of reference is something which is already there, which is O in all the cases. Okay. So those are small wedges and small cubes which you consider. So all that gets averaged out. Okay. It will simplify our discussion if instead of considering the general case of three-dimensional deformation, we focus our attention to a body whose particles all lie in the same plane and which deform only in this plane. So we only consider sort of this planar deformation. just for the sake of simplicity of analysis. Okay, just like in the previous case, we had started off with plane stress and so many things were easier to visualize. Same what we want to do over here. Okay, so this would be called as plane strain to start with. All the points and displacement lie on the same plane. All the displacements also happen in the same plane. And we'll return to three-dimensional analysis at some point later. Okay. Now, in figure 4.27, there you go. We have two examples in which a thin rubber block is deformed in its own plane. Okay, so this is the thin rubber block, and in its undeformed state over here in A, undeformed block of rubber, and there is this diagram drawn A, B, C, D, E, F, G, H. Okay, this is just to get a feel of what the deformation looks like. Then in 4.27b, all elements of the block have been deformed the same amount. We call this state as uniform strain. So this is a uniform strain over here. So they are deformed by the same amount. You can see the arrows. You can see how the remote or at the loads are applied at the boundaries. And just to mention over here, deformation can happen not necessarily by a mechanical load. It can happen due to, say, a thermal load as well, right? You can change the temperature and it will expand or contract. That is also deformation, and all that definitions are inclusive in this. And that is why when I say on the application of a load, it does not necessarily mean a mechanical load. It can be any sort of load which causes a deformation. Okay, so that's how you have a uniform strain, and you can see that there is definitely a change in this superimposed diagram as you move to P. Now, if you look at C, this is a non-uniform deformation. Okay, in the sense, it seems there is more happening on this side, more load applied on this side and less on this side. Okay, so that's the way it has compressed. In this case, the entire thing had the same load, so that's why it was uniformly straining. So this is called a uniform strain, this is called a non-uniform strain, just to get a idea of how it happens. Now you want to examine the uniform state of deformation in B, so I'll just remove these. You want to see the uniform state of deformation in 4.27b. We note that the originally straight lines are straight in the deformed case. Now look at the line GC. It continues to remain straight in the uniform strain condition. AE continues to remain strain, and so on. Yes, CG reduces in size, AE increases in size, but they continue to remain straight lines, all of them. Okay, not just these two lines. So by contrast, the lines BF and DH rotate equal and opposite amounts, and both change in length by the same increment. So BF and DH also rotate, and they will change by the same amount because of the symmetry of these two lines. Now further examination of 4.27b does not reveal any other type of transformation of an originally straight line. So if you look at 4.27b, it does not reveal any other type of transformation of an originally straight line, and in fact it can be demonstrated rigorously. We don't do that, but it can be shown that in uniform strain any originally straight line can only transform into another straight line. Okay, that is something which we will not be showing, but it can be shown. A straight line remains a straight line. Of course it can rotate, it can change in size, increase or decrease, but it remains straight line. Now you please move to 4.27d. In this diagram, you observe that the originally straight lines are not necessarily straight in the deformed state. Evidently, a line can remain straight, unrotated and unchanged in length, as is line AE. Okay, so AE, if you look, yes, it remains straight, and that is just because of the way you are applying the load. It is unrotated, it remains straight, but it has clearly changed in length. Most likely it has slightly increased in length. But the other lines, say the line, and the same would be happening to line CG. CG also seems to have its straight line intact, though it has reduced in size. Okay, but it is not true for the other lines. Okay. It may become a continuous curve whose arc length may or may not be equal to the original length. So if you look at the line BF and DH, they can actually become an arc. Okay, and that is what it means. Now the straight lines, all the straight lines do not remain as a straight line, and that is one of the characteristics of a non-uniform straight. So you cannot take like a couple of straight lines and just see. The idea must be that any straight line drawn must continue to remain a straight line, not just like a couple of special cases. Okay, so clearly the mathematical analysis of this is quite involved. Okay, and if we examine the deformation of a sufficiently small portion of the block in 4.27, say a small area centered on O, we observe that over this area the curved lines BF and DH can be replaced by their tangents. So I'll draw this slightly better. So I'm trying to draw this. So O is over there, and you have this BF line, which is say like this. So let me draw a better one, slightly harder with a pen. Okay, BF is like this, and say DH is like this. This is what it has become. This is the point O. Now we want to not leave this case out, this non-uniform strain. So what do we do with it? We say, well, for a region which is close to O, let's say this region. Okay, in this region, this curve can be replaced by a tangent line, and similarly this curve can be replaced by a tangent line. This is something which you have already done. Okay, I have already explained to you how this curve can be replaced by a tangent. Okay, so nothing new over here. And the deformations of the small area is then similar to that of this. So now there are all lines everywhere, and that's how this non-strain you can approximate, non-uniform strain you can approximate as a uniform strain if you focus on a very small area around your point of interest. That's the important part. So in this is the mathematical language of it. In the limit of the small area centered on O shrinks to 0, this uniform becomes the deformation at point O. Okay, so if you In the limit, the small area centered in on O shrinks to 0, and this is very similar. Remember the cube which you had in the previous case. Okay, delta x, delta y, delta z, and the whole point was that all these delta x, delta y, delta z eventually tend to 0, and that's why you could write, say, dou sigma x by dou x into delta x plus sigma x on the other face. Okay, so that's how you could do all these things. So you do a similar analysis over, and then you can say that the stress, well, on the faces is actually the stress components at that point. Okay, so in a similar way, the deformation which is around in a small area which is tending to 0 is actually the same as that of that point. So this is an approximation, and this you can only make in a continuous solid, continuum mechanics, where, as I have said before, that you just ignore things like the grain boundaries or the atomic configuration. There is no discontinuity anywhere in your visualization of the solid. Okay, so we now consider a thin continuous body. That's over here, I think. Yes. So we consider a thin continuous body which lies entirely in the xy plane. So that is shown by this OCDE. And let me just say it's a thin continuous body. Okay. Which lies entirely in the xy plane and which undergoes a small geometrically compatible deformation in the xy plane. So it undergoes a small geometrically compatible deformation in the xy plane. Remember what geometrically compatible deformation means for a three-dimensional solid or a two-dimensional solid? There are no voids. Okay, so there is no gap, there is no tearing of the paper, breaking of the object and things like that. So they can deform, but there is no voids anywhere. Okay, so with that, you see that the deformed element can be seen in figure 4.28. So E has become E dash, C has become C dash, O has gone to O dash, D has become D dash. And this is all happening in the same XY plane. All these displacements which you see are all happening in the same XY plane. Okay. So for the deform, let us, so now we want to, what we want to do is we want to quantify deformation. I mean, we know that deformation has happened, right? And O is our point of interest, like always, okay? And if you go back, you see what this 2 was, motion of points of a body relative to each other, okay? So we want to see the motion of O relative to its neighboring points. So we will always, when we define strain, we always utilize the neighborhood of the point of interest. And we want to now quantify, like give a number of how much deformation has happened. Okay, we know deformation has happened, but how much? So we want to find a way to quantify, and strain, as you will see, is a way to do it. Okay, so let us express the deformation in the vicinity of point O quantitatively by giving the changes in length of the two lines OC and OE. So look at the line OC and line OE. What you must do is try to track the change in length of these two lines. Okay, as I've said with respect to the neighbors, so we have taken these two neighbors C and O, C and E, and we shall find it convenient to define the dimensionless quantities which will describe these two aspects of the deformation. The first of it, which gives the measure of elongation, okay, let's take the first one, measure of elongation. Let me write in a slightly better font. Okay, and this is as good as it can get, it seems. Okay, so this gives a measure of the elongation, or contraction, okay, it's clear, of a line, and this will be called a normal strain component, and the second one will give us a measure of the relative rotation of the two lines, which will be called the shear strain one. Okay, so let's start with the normal strain one, measure of the elongation of the line. So this is defined, okay, as the fractional change in the original length of a line, and is designated by the symbol epsilon with a subscript to indicate the original direction of the line. Okay, so we have the symbol this for the normal strain as this epsilon in your textbook, but I'll just use a E. Okay, so and it will, over time you will find it comfortable using E as only. Okay, so let's start and just start with this, okay, with what is given in your book. So this is defined, remember this is the second time we are using this definition, as a limit delta x tending to 0 as O dash C dash minus OC divided by OC. Similarly, EY is defined as limit delta y tending to 0 and O dash E dash minus OE by OE. So that is how you have defined the measure of elongation, and it's essentially the change which has happened in this length OC and OE with respect to its original length. Okay, and let's go with the symbol now and we'll transform at some place. So this is called a normal strain, and it is evident that the normal strain will be what? It will be positive when the line has elongated, and it will be negative when the line has compressed or contracts. Okay, now look at the second case, which is about the measure of rotation of two lines. Let me put this word, relative rotation of two lines, and this is called a shear strain. So you see the words are common between stress, but I mean the what they mean and how you define them are like there's no relation whatsoever. There you start with the forces, here you start with the displacements. There's no commonality between the two. Okay, so how is this defined? Let me just write out here. Let me just rub it out first. So this is shown by the symbol gamma xy. As you may have guessed, the meaning is the same on the x plane in the y direction, but right now because it's a two-dimensional one, we are not worrying too much. Limit of delta x and delta y tending to 0, angle COE minus angle C dash O dash E dash. This is what gamma xy is. The difference between angle COE, which is what, 90 degree it seems initially, okay, and then the new angle C dash, O dash and E dash, this one. Difference between the two is called shear strain, and that is why it says a measure of the relative rotation of the two lines. If this angle C dash, O dash and E dash would have remained 90 degree, then you would have said there was no shear strain, okay, because there was no relative rotation. So this can be written as limit of again of delta x delta y tending to 0 pi by 2 minus angle C dash O dash and E dash. Okay, so these are again, I mean this is again a definition, so you don't, I mean to quantify deformation you have taken these two quantities, and this is how you have defined those two terms. Okay, okay, so there we sort of we have given a brief about what the two kinds of strain are, the normal and the shear strains. And the next step is how to actually relate the strain and the displacements in a plane strain condition. Okay, so plane strain is what we are using over here to stick to two dimensionality. And okay, there is one note which I should perhaps make over here. Remember, for plane stress, we required the body to be relatively thin. Well, for plane strain, you require your body to be really thick so that there is no displacement in the thickness direction. Okay, it's so thick that any displacement in the thickness direction will be negligible compared to that thickness. So that's why plane strain automatically translates to very thick. Okay, solid. So if your solid is very thick or relatively thick compared to other dimensions, you can make a plane strain approximation. So that's one note I thought which we should be clear about. Okay, so remember in the last sort of when we discussed stresses, we related how the stress vector was dependent on force. Okay, so there was a limit over an area, delta F by delta A was taken as 0, and then there was a plane n which you have to, the direction n of the plane which you have to consider. So that was sort of a relationship between stress vector and the force which applies over there. And that was an internal force because you had sort of virtually cut an object. Now you want to do something similar over here. You want to find a relationship between strain and displacements. And this is what we intend to do right now. So we have already seen what a displacement is, how it looks like. So let's say this, that if we let u be the displacement in the x direction of O in figure 4.28, okay, in figure 4.28, then the displacement of O will be equal to u I cap plus v j cap. Okay, and since it's a plane strain situation, you will not have a k cap. Okay, fine. So this is also shown in figure 4.29. You can see that. Okay, so this relation is illustrated in figure 4.29. So I'll show that how this O has moved to O dash. So this is the displacement vector. U is the component in the x direction, V is the component in the y direction. So that is what is shown over here. Okay. Now, one thing is that the displacements u and v must be continuous functions of x and y to ensure that the displacement be geometrically compatible. So u has to be a continuous function of x and y, v has to be a continuous function of x and y, and this continuity ensures that there is a geometric compatibility, in the sense there are no voids. Now, using the concept of partial derivatives, we can express the displacements of point E and C in figure 4.29. So let's see point E and C. So let's take E first. I'll just zoom in over here. So if O has displaced by V in, so we are considering only in this y direction now. if O has displaced by V in the y direction, E should have displaced by V plus dou V by dou y into delta y. Okay, and just like the previous case, in the y direction only. So that is what E and E dash so shows. Okay, this is the component in the y direction. Now this has, again, as I've said before, it can have higher order terms, but you ignore all that. So you just go with this one particular term. Okay, and partial derivative, because u and v both are functions of actually x and y, like it was the case in the previous earlier analysis as well. Similarly, if O has moved to O dash and the component in the x direction is u, you will have a u for E, you will have a u plus dou u by dou y into delta y. Okay, because this difference is over here between O and E. This is very similar to what we have done before. So that's how we are able to write the components of displacement of E in terms of the components of displacement of O. Very similarly, we will write the components of displacement of C in terms of components of displacement of O. So if O has moved to U, this has moved to dou U by dou X, because now you are moving in the X direction into delta X. And similarly, V plus dou V by dou X into delta X. Okay, so C has moved to the C dash, and these are the two components of this. Okay, so this is geometrically, I think, clear now, and you practically have where O has moved to O dash, E has moved to E dash, C has moved to C dash, and D has moved to D dash, but we are not worrying about that right now. I mean, we don't intend to write what that value is. So once this is done, we have to make an assumption that the strains are small compared to unity, and then we can write the normal strain. Sorry. Okay, so the normal strain Ex can be written as what is it? O dash C dash in the x direction, right? So you must take the change in length of this one, because you are trying to write the normal stress in the x direction. So it will be O dash C dash minus OC divided by OC, and this value will be equal to limit of delta x tending to 0. What is O dash C dash? Let's see. O dash C dash is this length. Okay, that is delta x plus dou u by dou x into delta x minus delta x by delta x. So let's see how this O dash C dash is written. So okay, OC clearly is delta x. Okay, so there is no doubt about how this and this has come up. O dash C dash must be written as this. So for that, you would want to, okay, I don't think, no, this is not delta x, this is actually u. We have already done that. Okay, this is u. Okay, sorry, I'm sorry, this is delta x. Okay, so that's there, and how do you now justify writing O dash C dash as this value? So let's see. Take this and take this, okay, and that would happen as, so the change in OC is, the length of OC is delta x, and you can write the O dash and C dash with respect to OC, and that you can write with a delta x plus dou u by dou x into delta x, just like in the previous cases. Okay, so this would give you something like dou u by dou x. Similarly, you will have a EY in which you will consider the normal strain for this element, and that would be equal to limit of delta x tending to 0 O dash E dash minus OE by OE. So OE is delta y, and O dash E dash will be delta y plus dou v by dou y delta y. So that would give you a dou v by dou y. And the final part about this shear strain, remember, is the change limit of delta x tending to 0, limit of delta y tending to 0, the change in angle pi, this angle, originally pi by 2, and finally this angle. Okay, so angle minus angle C dash O dash E dash, C dash O dash and E dash. So this you will see will come out to be dou v by dou x plus dou u by dou y. So you can check your book also. I mean, the diagram perhaps will be more clear over there, and you should be able to write this angle accordingly. Okay. Okay. So this is how you can sort of write this term, and okay. Now you must definitely try to see how these angles are written and how these values are written. You must find, like, really be convinced about this. Please don't leave anything at this stage in which you are not clear how things have come up around. Okay, so you should be very clear by this stage how the angle C dash O dash and E dash is actually written as is written in your book. Okay, so that's how it is given. So I mean, I'll just give you a hint that when you want to find this angle, what you must do is subtract from 90° this angle and this angle. Okay, so from 90°, when you subtract this angle and this angle, you will get this angle. So that is how you have to do. And how will you find this angle? Take a triangle like this, draw some sort of a tan or a tangent. So I think this value is clearly known to you. Okay, and this value you can easily find out, and that's how you can do this. Okay, so please be very clear about the geometry over here, and work out some of the things yourself. Okay, so that we don't have that situation that you have only learned formulas and not understood it. The reason you are learning this course in this way is to sort of have a greater understanding over this subject, and you will find it slightly difficult in the start, because especially when you are just planning to look at a lecture online and thinking that somehow it will diffuse into your mind, but that's not how it will happen. You will have to read the book, come back to the lecture, read the book again, understand it more, do everything word by word, line by line, equation by equation, term by term. Only then, and if you have any doubt anywhere, even for the smallest of the things, please do not hesitate to ask me. Okay, I'll be very happy to help you in that part. Okay, so we'll leave up over here. We have defined what Ex is. we have defined what EY is, and we have defined what gamma xy, which is the shear strain, is. So we'll continue with our discussions beyond this in our next class. So see you then. Thank you.